Every morning you wake up, it's there. You don't think about it. You make coffee, glance out the window, and it's already climbing over the rooftops, doing what it's always done. 4.5 billion years, give or take. The same star, the same light, 8 minutes old by the time it reaches your face. We've been studying the sun longer than we've had writing to record it with. We have spacecraft watching it in real time right now. We have temperature maps of its surface, magnetic field charts, decades of spectral data. If any object in the universe should feel known to us, it's this one.
In 2021, a spacecraft crossed into the sun's outer atmosphere for the first time in history. What it found there contradicted models we'd been building for decades. As it turns out, we didn't know what the sun was. But to understand what Parker found, you have to start with what we thought we knew. The standard model of the sun isn't a guess. It's the product of a century of physics, confirmed by helioseismology, neutrino detectors, precise spectroscopic observation. Nuclear fusion in the core, temperatures around 16 million degrees Celsius.
Energy radiates outward through the radiative zone, then churns through the convective zone, and finally reaches the visible surface, the photosphere, about 5,500 degrees Celsius. Bright, stable, knowable. And then you have the corona. The corona is the sun's outer atmosphere, the wispy halo visible from Earth only during a total solar eclipse. Thin, ghostly. And here's the thing that has bothered physicists for more than 80 years. The corona is nearly 200 times hotter than the surface directly below it. Not a little hotter, 200 times. The photosphere is 5,500 degrees.
The corona runs to 1 million degrees, sometimes 2 million. The fundamental rule of thermodynamics says heat flows from hot to cold, which means the corona should be cooler as you move away from the energy source, not hotter. That's not a subtle discrepancy. That's the model breaking down completely. It has a name, the coronal heating problem. Scientists first identified it in the early 1940s, and as of today, more than 80 years later, it is still not fully resolved. I remember when I first grasped what that means. Not the temperature number, but the implication. The star closest to us, the one we know best, is doing something we cannot explain every day. We just learned to live with that. Parker Solar Probe was built, in part, to finally get close enough to start answering this. But what it found on the way in, that was something else. So what does it mean to touch the sun? Not metaphor. There's a specific boundary. It's called the Alphen critical surface, the line where the solar wind accelerates past the point of no return. Inside it, plasma is still connected to the sun. Waves can travel back.
Материал является в реальном смысле частью солнечной атмосферы. Пересеки эту границу наружу, и ветер движется так быстро, что ничего, ни волна, ни сигнал не сможет преодолеть свой путь обратно к поверхности. Это край. Это то, насколько Солнце простирается физически. Десятилетиями ни одно спаскрафт не пересекало его. Мы даже не знали точно, где она находится. Оценки с помощью дистанционной съемки ставили его где-то между 10 и 20 солнечными радиусами от поверхности. Широкий запас. 28 апреля 2021 года 8-й пролет Parker Solar Probe над Солнцем прорвался. 18,8 солнечных радиусов от поверхности.
About 8 million miles from the solar face. To survive this, The probe uses a carbon composite heat shield. The shield's outer surface reaches approximately 1,370 degrees Celsius. Behind it, the instruments operate at roughly room temperature. The engineers at Johns Hopkins Applied Physics Laboratory built something that sits inside a star's atmosphere and does not melt. That deserves a moment. The spacecraft stayed inside the Corona for roughly 5 hours on that first crossing. 5 hours of data from inside the sun's atmosphere that no instrument had ever collected before. And almost immediately, the sensors picked up something that wasn't in the models: switchbacks. The name is almost too casual for what they are. Imagine the sun is constantly streaming magnetic field lines outward, billions of lines, all flowing away from the surface like water from a showerhead. In the standard picture, those lines flow smoothly outward with the solar wind. What Parker found instead? The field lines were folding back on themselves, reversing direction, almost 180 degrees, then snapping forward again, over and over, throughout the wind. Not a fluke, not instrument noise, a structure. The reversals last anywhere from a few seconds to a few hours. During a switchback event, the local plasma doesn't just flip direction, it also spikes in speed and temperature. Then it recovers. I spent a while trying to find a physical analogy that actually works. The closest I can get: imagine a river flowing steadily downstream. Now picture a section where for 100 meters the water is flowing upstream. Then it reverses back. And this is happening thousands of times simultaneously, everywhere you look. That's approximately what the solar wind is doing at close range.
Паркер обнаружил свитчбеки еще на свой первый пролет в ноябре 2018-го. Первые зацепки, впервые описанные командами под руководством Стюарта Бейла в Беркли и Джастином Каспером на Университете Мичигана. Но тогда это были всего лишь наблюдения, а не структура. Попадание в корону изменило картину навсегда. Они везде. Это не аномалии. Они кажутся фундаментальными для того, как юный солнечный ветер организуется близко к Солнцу. Здесь начинается истинная наука. Мы точно не знаем, что их создает. Две конкурирующие гипотезы доминируют в литературе.
One says they form in the outer corona through velocity shear, different layers of wind moving at different speeds, essentially causing the field lines to fold. The other says they originate near the solar surface through a process called interchange reconnection, magnetic field lines snapping and reconnecting close to the photosphere, launching the kink outward like a whip. Both models have data supporting them. Both camps have credible researchers. No consensus yet. What they might be doing, that's where it gets interesting.
The plasma acceleraция и temperatura spikes during switchback events look like they could be contributing to coronal heating, injecting energy into the wind. Maybe part of the answer to the 80-year-old question. Maybe. But switchbacks were only the first surprise. The solar wind itself turned out to be built completely differently from the textbook version. For decades, we classified the solar wind in two buckets: fast and slow. Fast wind, moving at around 800 kilometers per second, streams out of open coronal holes near the sun's poles.
Slow wind, at around 300 to 400 kilometers per second, comes from the equatorial regions. Clean division, useful model. Parker found something that doesn't fit this model at all. Close to the sun, before the wind has had time to fully develop and separate, the transition zone is far more structured and turbulent than anyone expected. The clean division between fast and slow doesn't exist yet. In its place, a chaotic, textured, intermittent flow,
that the existing models simply didn't predict. And in 2023, the European Space Agency's Solar Orbiter made an observation that may rewrite how we understand the source of the fast wind entirely. The instrument was the high-resolution Extreme Ultraviolet Imager. The target? Coronal holes, the dark regions in the Sun's atmosphere where magnetic field lines open outward into space. In those dark interiors, Solar Orbiter found jets, tiny, violent jets of plasma. Each one lasts between 20 and 100 seconds. Each one reaches speeds of roughly 100 kilometers per second. Each one releases energy in what physicists call the Picoflare range, somewhere between 10 to the 21st and 10 to the 24th ergs per jet. A single one of these is almost invisibly small on a stellar scale, but they're not rare. They're everywhere across the observed coronal hole. Constant, overlapping, ubiquitous. The team, led by Lakshmi Pradeep Chita at the Max Planck Institute for Solar System Research, published in the journal Science in August 2023. Their conclusion? These Picoflare jets may be producing enough high-temperature plasma to sustain the fast solar wind. The solar wind might not be a steady stream at all. It might be, at its origin, millions of tiny explosions per second, each invisible individually, collectively building the river that sweeps past Earth. And that river, that's where the story stops being abstract. Stop for a second. We are 8 light minutes from this star. It is the closest one, and we still don't understand how it heats its own atmosphere, or exactly how it launches the wind that flows through the entire solar system. There are 400 billion stars in the Milky Way. We have one with a probe inside its corona. One. And it is still giving us surprises. The solar wind doesn't stay near the sun. It fills the heliosphere, the vast magnetic bubble extending past Pluto, past Voyager's position, out to where the interstellar medium begins. Everything inside that bubble, every planet, every spacecraft, every astronaut in orbit, lives inside the sun's extended atmosphere, Earth included. When the wind is disturbed, when a large coronal mass ejection erupts and the shock wave hits Earth's magnetosphere, the consequences are not academic. Geomagnetic storms disrupt GPS satellites. They induce currents in power grids. They have knocked out satellites and damaged transformers. In 1859, a solar storm, now called the Carrington event, struck Earth. The technology then was telegraphs, and the current surge was so powerful that telegraph operators reported being able to send messages after physically disconnecting their batteries because the geomagnetic storm itself was powering the lines. Auroras were visible as far south as Cuba. In June 2013, Lloyd's of London and Atmospheric and Environmental Research published a joint risk assessment of what the Carrington event would cost today. Their estimate for the United States alone? Between $600 billion and $2.6 trillion. Between 20 and 40 million Americans, potentially without power, for up to 2 years at the upper end, while the damaged high-voltage transformers are replaced. Transformers that take months to manufacture and ship. And here is the thing that keeps coming back to me. In July 2012, a coronal mass ejection of Carrington-class intensity actually happened. It just didn't hit us. It missed Earth's position by approximately 9 days of orbital motion. 9 days. We are not separated from the sun by comfortable distance. We are inside its weather system. Parker is still out there. On December 24th, 2024, Christmas Eve, it made its closest approach yet, 6.1 million kilometers from the solar surface, moving at approximately 430,000 miles per hour, the fastest any human-made object has ever traveled. The heat shield absorbing temperatures around 1400 degrees Celsius, while the instruments behind it collected data at room temperature. The signal confirming it had survived arrived 2 days later. It has now completed multiple passes at this record distance. Each one, the instruments gathering measurements from deeper inside the corona than anything that existed before. Solar Orbiter continues its own mission in parallel, the first spacecraft to image the sun's polar regions directly, regions that no camera had ever seen because every prior spacecraft was constrained to the ecliptic plane. The poles of the sun, still largely unobserved, still largely unknown. What remains open? The coronal heating mechanism, still no consensus. The exact formation process of switchbacks, still contested. The full origin structure of the slow solar wind, still unclear. These are not minor footnotes. These are the central questions of heliophysics. When Parker transmits the full data set from its recent passes and the analysis teams work through it, there will be new findings. That's not a guess. Every previous data set from this mission produced something unexpected. There's no reason the deepest data won't do the same. We'll be going through it here when it arrives. Come back to that morning. Same sun, same 8 light minutes, same light hitting the same window. But now you know, out there, right now, the magnetic field lines in the solar wind are folding back on themselves for reasons we're still working out. The corona is burning at 1 million degrees by a mechanism we don't fully understand. Millions of tiny plasma jets, each one lasting less than 2 minutes, are possibly building the wind that wraps around our entire planet. The star is 4.5 billion years old. We have been watching it with instruments for about 100 years. We sent one spacecraft close enough to touch it, and it came back with questions we didn't know to ask. The closest star to Earth is still, in the most precise scientific sense of the word, unknown.